Hi, kids. So, normally back in the day, I used to do this as a lecture. So, this would be what we did in class. Now, I've gotten away from that. I don't think that's as useful of time. But what I'd like you to do is take out your notebooks, open up to a fresh sheet of paper, and label Unit 2 Atomic Theory. What I'm going to do right now is a lecture I normally did in class, but you're watching it at home. And I'm at home, so you get to see my window. Awesome. Hopefully. All right, so atomic theory. Now, what I'm going to do is bring you through a few scientists that helped us develop atomic theory. The first person's name is Dalton, John Dalton. So please write down his name, John Dalton. So, John Dalton, actually, you probably saw in that other YouTube video, he had noticed that when things combined, there always was definite proportions. So, as he was doing chemical reactions, he noticed that the same mass always reacted. So, for example, this is supposed to represent copper. If you had a mass of copper and you reacted it with a mass of oxygen, it would change colors, which means that it went through a chemical change. There's a chemical reaction happening here, and it changed its identity. And this is Statue of Liberty green, rust. And you know that, right? The Statue of Liberty is green because it came as copper. It's supposed to be skin toned from France, and it oxidized sitting out on New York Harbor, and it turned green. So we got this nice coating of what we call copper oxide on the outside. So John Dalton was noticing that every time he ran a reaction, he always ended up with the same mass. So he said that matter is actually made up of little tiny particles. And before Dalton, there was another person that had coined the term atom. And his name is Democritus. Now, Democritus, you may know, father of democracy. He was a philosopher. He did not run experiments. Instead, he just had an idea. He said, what if I took matter and I kept cutting it in half and cutting it in half and cutting it up? I think it will eventually be uncuttable, which is where we get the word atom, which means uncuttable. Turns out Democritus had no scientific backing. He is actually not a scientist, only a philosopher, and therefore we couldn't take his word for granted. We couldn't take his word because nobody knew. We wanted to prove it. Now, it wasn't until the Industrial Revolution when we actually started to look at gases and look at particles and look at the steam engine and actually take quantities for these particles. So, John Dalton did experiments and figured out the law of definite proportions, which says that if you have two things and you add them together, the sum of their parts will be equal to, the sum will be equal to their parts. So everything will always react in a definite proportion. So he said that atoms were like billiard balls. They were these hard spheres and they were bouncing off of each other. And every particle diagram we've drawn in class so far is Dalton's billiard ball model, where no matter what the particle is, we can make a sphere and show the particle that way, like this. All right. He called these building blocks atoms, which were like billiard balls, which we also call the hard sphere model. So Dalton's model of the atom is that atoms are hard spheres like billiard balls, and they're indivisible. Gonna want to write this down. Pause the video. No, pause the video. Okay, so elements are made up of extremely small particles called atoms. All right, so all elements are only one type of atom, and that type of atom is called an element. All right, so every type of atom, it's like the flavors when you go into Carvel. There's lots of types of ice cream. All of them are ice cream, but they're different flavors because they have different compositions. Same idea. Elements are all the same kind of atom over and over and over again. It's the types of atoms that we can have. So the periodic table of the elements tells us all the different atoms that we have, the types, all of the elements. Atoms are given of a given element are identical in size, mass, and other properties. So every atom of aluminum is identical to every other atom of aluminum. Atoms of different elements differ in size, mass, and other properties. So an atom of tin is very different than an atom of aluminum, but all of the atoms of aluminum are the same, and all the atoms of tin are the same. Now, this is true of every element on the periodic table. Number 3, atoms cannot be subdivided, created, or destroyed. Subdivided is blue because it turns out that's the part we're going to change. Everything else is true. But we're going to build on this theory and learn about other scientists that learn new things after this. So, atoms cannot be subdivided, created, or destroyed. The law of conservation of matter tells us that nothing can be created or destroyed. All of the atoms that we have on our planet, we have always had in our universe. So there's a definite amount of matter that exists in our universe. And that finite amount of matter was created during the Big Bang. So that's why it's an important event. Now, everything is just recycled. Nothing is created or destroyed. It can be transformed from a compound to an element to a different compound. But the atoms that we have are the atoms that we have. We can only recycle. Number 4. Atoms of different elements combine in simple whole number ratios to form chemical compounds. So, H2O is 2 hydrogens and 1 oxygen, always. There's no other way to make water. That's the proportion for water. They're combined in simple whole number ratios. You can't have a portion of an atom. A compound can be made up of multiple atoms. C6H12O6, glucose, right, has 24 atoms. C6H12O6, 6 plus 12 plus 18 is 18 plus 6, 24 atoms. It's a huge molecule, but they get much more complex than that. But atoms are the smallest building block. You can't break down an atom. In chemical reactions, atoms are combined, separated, and rearranged. So, when a chemical reaction occurs, atoms can move around, they can change who they're paired with, they can change how they're interacting, but the atoms themselves never change. They're just changing partners and how they're interacting, how they act, but their identity never changes. Did you write it all down? Make sure you write it all down. If you didn't, pause, write it all down. Our next guy is J.J. Thomson. J.J. Thomson ran an experiment with something called a cathode ray tube. A cathode ray tube is a vacuum sealed tube, so there's no air inside. And he took this high voltage electricity and he added this electricity to this tube. When he did that, he also added a positively charged plate here and a negatively charged plate here. Now, you have to realize that one thing is true. We had defined electricity and the terms in which we use for electricity before we defined the terms of an atom. So, sometimes we use terms for electricity to define an atom, but electricity actually comes from atoms in a weird way. I'll explain it in a minute. So, J.J. Thomson did this experiment, and he put electricity on these plates so that this plate had a positive charge, and this plate had a negative charge. Now, when he shot the electricity through the cathode ray tube, he noticed that this beam was always going pew, pew, towards the positive plate. And he knew that if it was going towards the positive plate, that opposites attract. So when we say opposite charges attract, positives are attracted to negatively charged objects. Positively charged objects and positively charged objects will repel. Negatively charged objects near negatively charged objects will repel. But a note on positive and negatively charged objects. It's not like a positive and negative in math. You can thank the founding fathers and Ben Franklin. because they did not know what was going on in electricity. And they thought that there was something happening mathematically with a positive and a negative. But you might as well name them Jim and Larry and say that Jims and Larrys attract and a Jim repel and a Larry repel. Positive and negative is not like in math where we went below zero on a number line. Positive is a factor that some substances have, and negative is a factor that some substances have. You call it chocolate and vanilla too, if you like. So we have chocolate charges and we have vanilla charges, and you can mix chocolate and vanilla, but chocolate and chocolate will repel, vanilla and vanilla will repel. I'm going to use a lot of these analogies. I want you to get out of your head that it's mathematically positive and negative. It's not the same thing as a negative value when you do a calculation. Now, since we know that positive and negative attract, J.J. Thomson said, there's something negative in the atom. There's something negative in the atom. But since normally atoms will move towards something positive or towards something negative, but normally most things do not have a charge, he came up with a model of the atom that looked different than Dalton's. He said there are charged particles inside of the atom. And he called those particles inside of the atom subatomic. Now, sub means below. The subway in the city is below. So he was thinking on the outside of the atom. If you go inside of the atom, things that make up the inside of the atom are called subatomic particles. And J.J. Thomson named the first subatomic particle. Now, it turns out that we didn't know all along that the reason that electricity was happening is it was this movement of a very small negative particle. Turns out we thought it was positive, we were all backwards, but it ends up that the negative particles that move through a wire that create electricity, we called electrons. So, J.J. Thomson imagined that there were these negative electrons and they were embedded in this positive dough. So instead of a billiard ball where it was all a hard sphere, it was more like, looked more like this, where we had these negative electrons and they were stuck in this positive dough. So J.J. Thomson, you have to remember, this is in the time of like Dickens, all right? So everybody knows A Christmas Carol and, please, sir, I want some more. This is what we're imagining, all right? So J.J. Thomson wanted to come up with an analogy, a way for people to think of this thing that had these negative things jammed in it that were stuck all throughout, that made it not have a uniform composition. Instead, it had positive dough and negative stuck throughout. His favorite dessert was something called plum pudding. Plum pudding is pudding made out of plums. It's very sweet. And it has big chunks of plum inside of this pudding. It's dessert. So a more delicious dessert analogy that I think you could get on board with is the chocolate chip cookie model, where you can imagine that the dough is all positive and there are those negative chocolate chips embedded in the system. So when you put it through the cathode ray tube, all of the negatives would go towards the top and be attracted to the positive. Side note, cathode ray tube is how an old school TV works. There was a detector screen on an old school TV, and we would shoot electrons at that fluorescent screen. Kind of like a typewriter, all the way down to make the screen. So inside of an old TV is a cathode ray tube, which is why sometimes the TV was called the tube, which is why you're watching me on YouTube. Stay tuned for part 2. I'm going to do another whole thing. All right, bye kids.